So in our next section, we're going to talk about the specific components that make up the Unified Computing System, or UCS. What are the different types of blades? What are the different types of chassis? How do the fabric interconnects work? How do the I/O modules work? And so on and so forth. You can see the specific details of this if you go to cisco.com/go/UCS. So we'll be looking at this for the individual part details of what is available now, as what parts are orderable, what's end of sale, what's end of life in terms of the system. But overall, we can kind of break this down into 5 main components. So first we have the blade chassis, which is going to be the physical enclosure that's going to hold the actual servers. We have the blade servers themselves, which are going to be the CPUs, the memory, the network adapters, potentially the hard disks that are going to be running the actual OS. We then have the I/O adapters, which are the network cards of the blades, which would be like our Cisco virtual interface card or some of the other vendor cards that go into the blades. We then have the input-output module, or the IOM, the I/O module, which is, we'll see, very similar to the fabric extenders for the Nexus 2Ks. It's essentially the same as the Nexus 2000, but it's in a different form factor that physically plugs into the Blade Series chassis. And then last but not least, we have the fabric interconnect, which is going to be the control plane and the management plane to the system, essentially the Ethernet switches and the fiber channel switches that are going to be used for all of the physical connectivity from the upstream network down to the downstream servers. Okay, so as I mentioned, first we have the blade chassis itself, which is going to be the physical enclosure. This is where you would plug the power supplies in. This is where you plug the fans in. And then ultimately, this is where the physical servers plug in. This is where the I/O module plugs in, essentially how you're going to wire the chassis. Okay, so let's go over to the product page, like I mentioned, which is cisco.com/go/UCS. And then in this section, we're going to be focusing on the B series blades. We'll come back later and talk about the C series standalone rack mount servers, and then what are some of the other miscellaneous options that they have as part of the overall portfolio. But if we go under B series blades, and then we go to compare models, this is going to be the actual physical servers that are going to make up the system. So right now there's mainly 4 models that are currently for sale. Okay, they start with B is going to be for the Blade series chassis, C is going to be for the standalone ones. So generally, the entry-level servers are either B200 or B200 and B22, and then they have equivalents in the C series servers, the C200s and the C22s, which are going to be the not necessarily small servers, but as compared to some of the other options, they're not going to be as powerful. But if you look at just the physical form factor of the servers, the way that the physical chassis system works, which is the B5108 blades, or the blade chassis, we have 2 views of the system. So here we have the components from the rear, and then we have the components from the front. So this is the blade chassis. And you can see that it has 8 different slots in order to hold the servers. And the servers come in 3 different form factors. We call them half width, half height, full width, half height, and full width, or actually it would be double width, double height. Ultimately, this depends on how many physical servers that you can plug into the chassis. So the one on the left here is going to be a half width, half height blade. So physically, we can fit 8 of these into the chassis, where these are slots number 1, 2, 3, 4, 5, 6, 7, 8. Then in the middle here, there's like a little divider between the backplane of the system. This physically pulls out on a per slot basis, which allows you to install a full width blade. So in the case of the full width blades, you would be taking up slots 1 and 2 at the same time, or 3 and 4, 5 and 6, 7 and 8. So in the case of the half width, half height blades, you can fit 8 of them into the chassis. The full width, half height blades, you can fit 4 of them. And then finally, the full width, double height, you can fit 2 of them. But basically, they're essentially the same servers, but they have, you could think of it as kind of like clustering the servers together, but from a layer 1 point of view. So for example, if we look at the B460M4, which is the largest of the servers, you'll see that on the front of it, physically, there is like a clustering connection that's used to connect the multiple motherboards of the servers together. So really behind the scenes, it's physically 4 half-width blades, but from the OS's point of view, it sees it as one individual server. So you don't install 4 copies of Windows or 4 copies of VMware, Linux, and so on and so forth. There's essentially custom Cisco chips that are interacting with the Intel chipset in order to allow the CPUs and the memory to think that it's essentially one giant board, as opposed to being 4 individual servers. But mainly, as you could probably guess, the big difference between the servers is going to be, first off, what are the number of processors that they can hold. So we can see for the half-width ones that are on the left, we can generally hold up to 2 processors. Okay, so that would be for the B200M2 or for the B200M4, where the M value is the generation of the blade. So this is Gen 3, this is Gen 4. So these half-width blades can take the middle range processors, which are the E5s. This would be the equivalent of like your i5 desktop processor. So it's not the low end like the Core i3, Core E3. It's the middle range one. So you can fit up to 2 processors. We can fit up to 768 gigs in the Gen 3, 1.5 terabytes of RAM in the Gen 4, and then physically up to 2 slots for disks. So they can run RAID is either a stripe set, which would be RAID 0, or a mirror set, which is RAID 1. Because as we know, with the physical disk capacities, in order to do a stripe set with parity or a striping mirrored set like a RAID 10 set, we would need more physical disks. Okay, so when you start to get into the larger servers like the 460 or the 420, you can see that physically those can handle more internal disks. So the B420M3 can handle up to 4 physical disks, and then those can run as either a stripe set, a mirror set, a parity set, which would be RAID 5, or a striping mirror set, which would be RAID 10. And then really what the main difference is going to be is as you start to go to the right into the bigger blades. The larger ones, the 460M4 and the 420M4, these are the ones that can handle the newer processors, or I should say the 260 and the 460 are the ones that have the E7s, where E7 would be the equivalent of i7, like the high-end desktop processor. In this case, this is the high-end server processor, which means ultimately that it can address more memory. So for 460M4, we can have up to 6 terabytes of RAM in the single server, so up to 96 sticks, getting us a total of 6 gigs of RAM. So it's going to be for generally very high I/O workloads, like bare metal database, for example, would be a good candidate for the 460M4, where the half-width blades, typically you use those for like virtualization, ESXi, Hyper-V, KVM, etc. But effectively, just like any differences in the pizza box servers, main big functional difference is going to be what CPU does it take, how many sticks of RAM does it take, and then what is the speed of the bus that is running at in terms of the CPU clocking, and then also the memory. But again, the big point about this is that based on the physical form factor of the blade, that's going to control how many that you can fit into the system. So in our particular case, we have a mix of B200M3s, B200M4s, and B22s, which I think are both M3 and M4. So we're going to have 2 chassis total in our examples. Each of them are fully loaded with 8 blades, and then we'll see that from a functionality point of view, the physical server details of the system don't really matter, because that's going to be one of the big flexible designs of UCS, that it kind of decouples what's going on in the physical hardware versus your configuration and how you're logically addressing the system from the service profiles. But really, at the end of the day, there's nothing too special about the blade chassis itself. It's just an enclosure for the servers. What the main advantage of doing it this way as opposed to having the standalone rack mount servers is that it cuts down on your physical cabling. So for each of these individual servers, notice that on the front of them, there's no ports for network connectivity. Like there's no RJ45 ports or regular SOPs for your 10 gig or your 40 gig attachment. Where that's going to happen is on the rear of the system, which is going to be the input-output module, and then its physical wiring up to the fabric interconnect, or the FI. So instead of having each of the individual servers have two physical cables that are going to be for LAN traffic and two physical cables that are for storage traffic, like our NICs and our HBAs, we're essentially running regular LAN connectivity and then FCOE connectivity over the fabric backplane, like the bus of the server or the bus of the chassis. And then all the cabling is coming out through the back through the I/O modules. I/O modules are physically uplinking to the fabric interconnects, and then the fabric interconnects are going to be the Ethernet switches, the storage switches, and then the management plane where we're connecting to the GUI and the CLI in order to actually provision and configure the system. So we'll see that one of the most important points of the system here is that without the fabric interconnects, the servers can't do any connectivity. You can't plug them in standalone like you could just a normal rack mount server. You have to have all of the entire components for the system to work. Okay, so the blade chassis to plug the servers in, obviously, the blade servers themselves, the adapters that are going to go on the blades. We'll take a look at this in more detail when we look at LAN connectivity. And then the input-output module, or the IOM. Okay, the IOM is sometimes also referred to as the fabric extender, or the FEX. This is where we have the physical connectivity from the fabric interconnect down to the chassis. Okay, then last but not least, we have the actual fabric interconnect, sometimes referred to as the FI or the UCS FI. And like I mentioned, this is hosting the management plane. So that's where the UCS Manager GUI is running from. The CLI is running from there. The API calls that we could do in terms of like XML and the other API interfaces. But essentially, it's going to be the single point of control that without the fabric interconnects, you won't be able to pass any traffic down to the physical servers, both from a LAN connectivity point of view and from a storage connectivity point of view. So when we wire the system, the fabric interconnects, there's going to be two of them for each of the blade chassis. So we have the A fabric and we have the B fabric. And then we have I/O module A and we have I/O module B. Okay, so for redundancy, there's going to be two fabric interconnects. There's going to be two input-output modules. The I/O modules plug physically into the back of the chassis. Okay, you can see this is where the fan trays are. This is where the power supplies are also located. And then from the I/O module, we're physically going to plug those cables up to the fabric interconnect. Okay, so in this case, these are 10 gig ports. This is the second generation I/O module, which is the 2208, which has 8 by 10 gig upstream and 32 by 10 gig downstream towards the blades. Okay, there's currently a third generation as well, which uses 40 gig attachment as opposed to 10 gig attachment. And then beyond that, there's also going to be a new fabric interconnect that's currently on the roadmap, hasn't been released yet, as of April of 2017, which directly interfaces or directly integrates with the ACI solution, where essentially the fabric interconnect is going to be an ACI leaf. So the network connectivity would be controlled from the APIC controller. So in terms of our like endpoint groups, our interface policy groups, and so on and so forth, and then the server details would be controlled from the UCS Manager. But again, from a physical connectivity point of view, I/O modules plug up to the fabric interconnect. The fabric interconnects themselves are then going to have a set of cluster cables that go from the L1 port over to the other L1 port. Okay, so this is like a regular Cat5 cable. So from L1 to L1, from L2 to L2, then behind the scenes, this is going to form a 2 by 1 gig port channel. And this is how the system is synchronizing its configuration between the two fabric interconnects. Now we'll see from a design point of view, one of the big things to note here is that this cluster link going east-west between the fabric interconnects, it's not the same as a VPC peer link, as we had previously seen in the Nexus 5Ks, the 7Ks, or the 9Ks within the ACI system, the cluster link is only used for synchronizing the management plane of the system, which is essentially just the config. It's not for synchronizing the control plane, which would be like the MAC address table or the any of like the storage table, like the Fabric login table. So we'll see that when we make configuration changes on the UCS, in general, anything that you do that is related to LAN connectivity or storage connectivity, you need to do it twice. Once for the A Fabrics configuration, and then once for the B Fabrics configuration. So we'll see that since, even though we're managing them both from one interface at a time, you still have them as separate physical boxes that you need to touch. So what I mean by this is that if we were to say for the Fabric Interconnect A on the left, let's say that this very last port is going up to our 5Ks as a LAN uplink. If we configure trunking on this port from Fabric Interconnect A point of view, it doesn't necessarily mean that that same port number that is on Fabric Interconnect B would be configured the same. Okay, so some of the configuration is going to be kind of redundant that we have to do it multiple times. Okay, so again, going back to our physical topology then. So the Blade Series chassis, this is where we have the input-output module, the I/O module. So we have IOM-A, we have IOM-B. In my particular case, these are going to have two cables. So these are 2 by twin-X cables. So they're the copper 10 gig. These go up to the Fabric interconnects. The Fabric interconnects then have native fiber channel ports that are going to be used for our storage connectivity. And then we have regular 10 gig Ethernet interfaces that are going to be used for our regular LAN traffic. Okay, so like our IP traffic, like web browsing. And then it's also going to be used for fiber channel over Ethernet. Okay, so the interfaces can be used for LAN and for SAN, which essentially makes this a unified platform, okay, or that it runs unified fabric. So we'll see that in terms of the physical connectivity, there's not that many options or not that many designs that you would typically go through from a layer 1 wiring point of view. And then that's going to affect how we're configuring our storage network, how we're configuring our LAN network. And then we'll take a look at those further details once we start to get into the actual LAN connectivity and the storage connectivity. Okay, but if we take a look again back at the product page, so let's go to, again, cisco.com/go/UCS. Then let's go down to view all products. Okay, so in B series, we have the actual blades, okay, the blade servers. We have the chassis, which is the 5100 or the UCS Mini. We have the actual adapters. Okay, so like VIC 1380 is going to be one of the newer cards. VIC 1240 or 1280 were the common Generation 2 cards. And then we have the actual Fabric interconnects. Okay, so 6300 is the current generation. The one that we're going to be using in this example is 6200, which is Generation 2. From a configuration point of view, there's no difference between the two of them in terms of what features they support. The main difference is going to be the bandwidth access to the fabric, where the 6300s are the 40 gig versions, the 6200s are the 10 gig versions, so 40 versus 10, obviously going to be more bandwidth. But in terms of the UCS manager, there's not really going to be a change when we're using one versus the other. It's just going to be a physical change in the chassis. Okay, so then we have the Fabric extender for the blade servers, then the Fabric extenders for the rack server. So these are talking about the regular Nexus 2Ks. The Fabric extenders for the Blade Series chassis, this is the input-output module or the I/O module. Okay, so again, under the Blade Series chassis, we have the 5100. And they used to have, let me see, I'm not sure if it's linked anymore here. They used to have a 3D model, but it was a Java app, but I think that they don't actually offer it anymore. But this is what the front of the system looks like. So this is where you physically plug the blades in. Okay, so they're, like a full rack deep. You physically slide it into the chassis, and then there's a locking arm that closes on the front of it. And then the chassis is physically going to have the input-output module plugged into it. Okay, so under fabric extenders, we have the 2208, which is the 8 by 10 gig. We have the 2204, which is similar to 2208. It's just 4 uplinks as opposed to 8 uplinks. And then I want to say that there is a 2300 as well, which uses 40 gig ports. But I'm not sure why it's not listed on this page. Then we have the fabric interconnects. Let me see if this 3D model works. There we go. Okay, so this is the fabric interconnect. Fabric interconnect, you can basically think of it just a switch. So it's an Ethernet switch, it's a storage switch, but it's running a special version of code that is going to be different than the normal NXOS CLI. So we'll see that the NXOS CLI does exist inside the UCS manager. We'll be able to log into the CLI and then run commands like show interface status, show interface trunk, show port channel summary, same stuff that we've done on Nexus 5K and 7K. But it has the additional software package, which is the UCS manager, the GUI, and then the APIs in order to actually configure the server portions of the network. But physically behind the scenes, the UCS 6200 fabric interconnects is the same as the Nexus 5500 switches. So it's physically the same box, it's just running a different version of code. Okay, so if you look at them side by side, you'll see that they look 100% identical in the data center. So in this case, this is a 6296, which it has 3 fixed banks of ports, and then it has 3 expansion slots. And any of these interfaces can run as either 10 gig Ethernet, and they can also run as up to 8 gig fiber channel. So like we saw in storage connectivity with the 5500s, the 5600s, they have unified ports, which means you can change them from Ethernet to fiber channel mode. But just like in the case of the Nexus, we do have a limitation where when you are configuring the fiber channel ports, they need to start from the right of the port bank and work to the left. And then the Ethernet ports start from the left of the port bank and work to the right. So essentially, the system has 4 modules in this particular case. We have the fixed module, which is going to be the ports on the right, and then we have expansion modules number 2, 3, and 4. So each of these can do their own numbering for fiber channel. Like you could say module number 3 is going to be used just for storage, and the rest of them are going to be used for Ethernet. But within the individual module, you have that requirement where Ethernet starts on the left and then fiber channel starts on the right. So typically, from a real design point of view, this is something that you want to provision before you bring the system up, because it does require a reboot of the fabric interconnects in order to change the mode from Ethernet, which is the default, to native fiber channel. Okay, we'll see that if we're running fiber channel over Ethernet, you don't require a reboot because the interface is still going to run in Ethernet mode. And it's essentially going to run the same storage protocol. It's just over an Ethernet tunnel as opposed to the native fiber channel encapsulation. Okay, so let me see if I can get let's see if it'll add the blade chassis to this as well. They used to have it as just one. It's one individual one. Let me try under, let's see, the VIC card doesn't have one. No, I'm not 100% sure if they have it listed here anymore. But essentially, the UCS Fabric Interconnect is going to be like your top of rack switch. It would be the replacement typically of like your 5K leafs or your 9K leafs. So it's the access switch that's connecting downstream to the servers. The main difference is that we're controlling all of those servers from one interface. And then if we want to move the OS from one physical blade to another, the system allows portability for that through a feature that they call the service profiles. So we'll see one of the big functional differences of the UCS system versus other blade management systems like HP Blade Chassis, IBM Blade Chassis, is that there's a lot of levels of indirection and virtualization built into the system, where it's trying to decouple all of your logical configuration from the underlying physical servers. So logical configuration being like, how many network adapters do I have? What VLANs are they going to use? What vSANs are going to be used for storage? Am I booting over the fiber channel network, the FCOE network? Am I booting to iSCSI? What is my disk configuration in terms of like RAID? What are the requirements of the server in terms of how many cores of CPU do I need? How much memory do I need before I can actually use the system? So a lot of this is going to be automated from the physical world to the logical world. So we're going to configure essentially the logical properties of the server, and then the system behind the scenes goes through a process called association, which essentially is programming those changes, essentially flashing the chips of the server blades in order to program what's the MAC address, what's the port worldwide name, the node worldwide name for storage connectivity. So we'll see that in addition to kind of virtualizing the cabling through the I/O module and the Fabric Interconnect, we're also going to be virtualizing the configuration of the system, separating the logical functions and the physical functions. Okay, there's a question here. Do you only need to reboot the main module and not the expansion cards as in the Nexus 5000 series GEM module? Yes, that's correct. So if we go back to that interactive model of the Fabric Interconnect, when you look at these individual expansion modules, like we have slot number 3 here that has 2, 4, 6, 8, 10, 12, 14, 16 each additional ports. And let's say that you wanted to make the bank of 4 ports here, so 13, 14, 15, and 16. If we wanted to run these as native fiber channel, it only requires that you reboot that individual module as opposed to rebooting the entire system. The issue comes in, we'll see, is that if we're trying to configure native fiber channel on the built-in module, so if it's module number 1, which is the one on the bottom, then this does require that you reboot the entire system. Okay, but we'll look at that from a configuration point of view once we get into our next sections. Okay, any questions up to this point in terms of the physical components of the system? So again, 5 components. We have the blade chassis enclosure, the servers themselves, the adapters of the servers, like the network card, the I/O module that physically plugs into the chassis. That's what we wire up to the Fabric Interconnect, and then the Fabric Interconnect is going to be the LAN switch and the SAN switch that we use to physically get traffic from the northbound network into the southbound access servers.